Hi, my name is Brian Caffo. I'm in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health, and this is Mathematical Biostatistics Bootcamp, Lecture 7. In this lecture, I'm going to talk about some common distributions. So in this lecture, I'm going to talk about basically three distributions, and really two if you kind of think about it. So the Bernoulli distribution is one, the binomial distribution, which is a distribution based on the Bernoulli distribution. And then I'll talk about the Gaussian or normal distribution, which is a very important one as well. In fact, I think if all the distributions were to get together and nominate a king, it would definitely be the normal distribution. So the Bernoulli distribution is named after Jacob Bernoulli. We've already talked about it before, but let's formalize it a little bit and remind ourselves of some of the notation. So Bernoulli random variable is just a fancy name for a coin flip. So Bernoulli random variable takes values 0 and 1 with probabilities p and 1 minus p, where p is some number between 0 and 1. So the probability mass function for a Bernoulli random variable we've seen before. It's the probability that x takes the specific value 0 or 1, and it's p to the x 1 minus p to the 1 minus x. The mean of a Bernoulli random variable is simply p, and the variance is p times 1 minus p. Facts that we've proven before, but we're just restating them now. And in general, for Bernoulli random variables, if you code a coin flip as a 1 or a head, it's often people call that a success and 0 as a failure, and they tend to do this regardless of whether the classification is actually something that's actually successful. So we might call a person getting side effects from a medication a success in terms of the Bernoulli coin flip. It's just a little bit of odd nomenclature, I guess. We've also already talked about the Bernoulli likelihood function. So if we have x1 to xn are observed data points, so the x1 to xn in this slide are numbers that we recorded, a collection of zeros and ones, then the likelihood is the product, because we're going to model these as independent coin flips, the product of p to the xi, 1 minus p, to the 1 minus xi. We've already talked about this equals p to the summation xi, 1 minus p to the n minus summation xi. So notice again that the likelihood only depends on the sum of the x's, so the total in each x is 0 or 1, so the sum of the x's is just the total number of successes. And then n minus the sum of the x's is the total number of failures. So if you know n and you know the total number of successes, then you know the Bernoulli likelihood. It doesn't matter what order the heads or tails occurred as far as information is contained in the data about the parameter p. Because n is fixed and assumed known, this implies that the sample proportion contains all the relevant information that you need to know about p insofar as the likelihood codifies it, simply because summation xi and summation xi over n are 1 to 1. You can get from one to the other easily by either multiplying or dividing by n. So the sufficiency result is basically that the proportion of successes is all the relevant information you need to make Bernoulli inference about a parameter. Now, again, this all depends on the model being correct, that you have correctly modeled the data as IID Bernoulli. We also, when we talked about maximum likelihood, we also showed that if you maximize the Bernoulli likelihood over p, then you obtain that p hat, which is summation xi over n, is the maximum likelihood estimator. And here's, we went over an example. So here, just to give you an example of Bernoulli likelihoods and what they look like, imagine if we flipped a coin 4 times. So if we flipped a coin 4 times, there's only 4 possible sufficient statistics that we could obtain. We could get 0 heads, 1 head out of the 4 coin flips, 2 heads out of the 4 coin flips, 3 heads out of the 4 coin flips, or 4 heads out of the 4 coin flips. And here is the 4 possible likelihoods that you could obtain from this experiment. And they're all normalized to have height 1. So here's on the leftmost one is the likelihood you get if you had no heads. The second one, you see it shifted a little bit to the right? And its peak is going to be right at p hat at a quarter, okay? And then if you get 2 heads, then you see the peak, the MLE in this case, is right at 0.5, and the likelihood shifts a little bit to the right. And if you've gotten 3 heads, it shifts a little bit more to the right. And if you've gotten 4 heads, then it shifts closer to 1. Notice, even in the event that you get all tails or all heads, the likelihood is not entirely at 0 or entirely at 1. Right? There's substantial uncertainty, right? The likelihood is correctly codifying the information that it's possible, even if the coin is, say, fair, here's the likelihood point right here, even if the coin is fair, to get 4 consecutive tails. And, it's just much less likely than if the coin is unfair towards some value closer to 0. So the likelihood, it's not entirely shoved up against the vertical line at 0. And it just gets closer and closer to that vertical line as you continue to flip and get tail after tail after tail. Binomial random variables are nothing other than the sum of IID Bernoulli trials. We've seen that the key variable from a Bernoulli experiment is the number of heads. So why don't we just create a random variable that is the number of heads? So in specific, if x1 to xn are IID Bernoulli, then the random variable x, defined as the sum of the individual xi's, is a so-called binomial random variable. And the binomial mass function is just the probability x takes any specific value, is n choose x, p to the x, 1 minus p to the n minus x, where p is the probability from each of the Bernoulli coin flips. Here, the values that x can take are 0 if every single coin flip was a tail, all the way up to n where every single coin flip was a head. Just to remind everyone, the notation n choose x, right, this parentheses n over x, n parentheses, this is n factorial over x factorial n minus x factorial. Here, 0 factorial we're going to treat as 1. And this formula counts the number of ways of selecting x items out of n without replacement, disregarding the order of the items. Okay, so let's consider an example. Imagine I have 10 neckties, and I pick out 3 and put them on my bed, let's say. And I'm not caring about what order on my bed from left to right or something like that. And so 10 choose 3 is the number of different configurations of ties that I could have obtained by picking 3 ties out of my 10 possible. So that's an example. I can't think of any reason why you would want to do this with your neckties, but whatever. So it's very easy, in fact. Certain special cases are very easy. So imagine if I was only picking 1 necktie, right? How many different combinations can I get? Well, intuitively, we know that answer has to be 10, right? Because, there's only 10 possibilities. Well, if you plug into the formula, you have 10 factorial divided by 1 factorial, which is just 1, n minus x factorial, which is 10 minus 1, or 9 factorial. So we have 10 factorial divided by 9 factorial, which is just 10. Okay? Another quite useful one is choose 2. How many ways can you pick 2 things out of n objects? That one seems to come up a lot in my daily life for some reason. And so that's, in this case, would be 10 factorial over 2 factorial, which is just 2, right? 2 times 1. Then divided by 8 factorial, right? So that's 10 times 9 divided by 2. So, at any rate, the general rule is for n choose 2, you just want to take n times n minus 1 over 2. And at any rate, it's one of the ones that it's worthwhile just to memorize the formula for that special case, because it seems to pop up a lot. So why is that factor? Why is n choose x the factor out in front of a binomial mass function? So let's now consider the possibility of getting 6 heads out of 10 coin flips from a coin with success probability p. Well, if you account for the order, if you say, what's the probability of getting tail, 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 that's 4 tails, then the remaining are heads, right, in that specific order, right? We know what that probability is. We would just plug into the multivariate Bernoulli mass function obtained by multiplying the Bernoulli mass function for each coin flip in order. And we would get p to the 6th, 1 minus p to the 4th. And as we know, because of the fact that it's only the total number of heads that's sufficient, that if it wasn't just the first four coin flips that were tails, if it was the last four coin flips that were tails, and the first six were heads, then we would get the same number. We'd get p to the sixth, 1 minus p to the fourth. And if we had the four tails sprinkled in any configuration of the six heads, then you will still get the same possible answer, p to the sixth, 1 minus p to the fourth. The result is that basically for any collection of instances where you get six heads and four tails, no matter what the order is, the probability is going to be p to the sixth. So what we need is to count how many such configurations there are. Well, in this case, there's 10 flips and with 10 positions that could be heads, and we want to know how many different collections of positions we can obtain. And that's just 10 choose 6. It's just exactly the necktie problem, but now we're picking the position of the coin flip that is a head, right? And so in this case, there's 10 choose 6 possible orders of 6 heads and 4 tails. We don't actually have to go through the specific construction of the binomial distribution because I think that's a pretty clear demonstration. That's how you would wind up with the probability of the sum of a collection of 10 Bernoulli random variables being 6, right? You would sum over all the possible ways you could get 6 heads, and it turns out that they all have the same probability, p to the 6, 1 minus p to the 6. So we just need the number of things that go into that sum, and it's pretty clear that it's 10 choose 6. So yeah, we only did this for a specific instance here. I hope you can see that if 10 instead was n, and 6 instead was x, that you would wind up with the same answer. N choose x, p to the x, 1 minus p to the n minus x. So that's the motivation. And you can actually mathematically check that the binomial mass function sums to 1. In fact, it's actually kind of a relatively famous formula, the binomial sum. And so if you, for example, look up on Wikipedia the binomial sum, you'll see that it just exactly illustrates that formula by itself tells you exactly that the binomial mass function sums to 1, but we're right now just going to trust that we did our calculation right. So let's just go through an example of using the binomial mass function. So suppose you have an intrepid friend that has 8 children, and it turns out that 7 of them are girls and none of them are twins. And so if you're very parsnickety, let's just forget about all the little parsnickety things that you could possibly think about related to this problem, like having twins. So let's just think about the problem in the conceptual way. We're going to think of every child from this family, its gender being a coin flip. And the question is, what's the chance of getting 7 out of 8 children that are girls if it really is the case that every child, their gender is independent from the other children and that there's a 50% probability at each birth of having a girl? And so what's the probability of getting 7 or more? Well, that's the probability of 7 or more is the probability of getting 7 girls out of 8 plus the probability of getting 8 girls out of 8. And so in this case, for the fair coin, it would be 8 choose 7, 0.5 to the 7th, 1 minus 0.5 to the 1. And then 8 choose 8, 0.5 to the 8, 1 minus 0.5 to 0. And, check with your calculator or even better with R, that you can get this number. It's about 4%. This is an example of using the binomial formula. I wanted to mention this particular example because this calculation is an example of a so-called p-value. And a p-value is always the probability under a null hypothesis of getting a result as extreme or more extreme than the one actually obtained. So the logic behind the p-value in this specific instance is that you have this evidence here that you think, wow, 7 girls out of 8 children, that seems pretty odd. Maybe the 50% chance of girls versus boys for this particular family is off for whatever the reason. So the p-value is saying, okay, well, why don't we calculate the probability, if the null hypothesis was true, of getting an event this extreme? And if that probability is very low, then maybe that's an indication that our hypothesis that the 50% is correct is not right. So at any rate, we'll talk about p-values later. Well, I hope we'll get to talking about p-values later. But I just wanted to mention that that's where the intuition behind this calculation is coming from. Right now, we're only using it as an illustration of plugging into the binomial formula. but I wanted to foreshadow kind of an important statistical technique. And then here in this page is the likelihood associated with P for this particular binomial experiment, if we're willing to model births as if they were binomial. And so here you can see, 0.5 is in the 1/16th likelihood, but not in the 1/8th likelihood. And then you can see, that this likelihood is far more peaked around 7/8, or it reaches its maximum at 7/8, and then the curvature of it sort of gives you a sense of the relative evidence for the collection of possible values of P.